Okay, so here we have a pretty fun problem. Let's analyze it first. Albert sings the note A, and Dr. Bissell is moving. So let's draw it out. Right? Let's draw it out. This is going to be Albert, right? It's going to be Albert, and he's singing the note A. Okay? Dr. Bissell, on the other hand, is moving directly towards Albert. With a velocity such that the note that he is hearing is a tritone above A. So that's going to be D sharp. No, I don't like that. That's going to be E flat. Okay? Determine the speed. So we're trying to determine the speed of the observer in miles per hour at which Dr. Bissell must approach Albert, right? We want him to hear this perfect E flat, and assuming that Albert is singing this perfect A. So what do we got to know? We have to know the speed of sound, right? So let's go ahead and derive that, right? So the speed of sound is going to be the square root of the bulk of the modulus of the medium divided by the density of the medium. Okay? Essentially, to have any mechanical wave propagate, we need to have a medium. So for sound, that's just going to be air. And for air, that's going to be rather easy because we can say that this bulk is just approximately equal to the ratio of specific heats for air, which is going to be 1.4, right? Just remember that. Multiplied by the pressure. So substituting that into our equation, we have V is equal to, right, gamma times pressure divided by the density of air now, okay? Let's continue, right? We can solve for pressure right here with the ideal gas law, right? So the ideal gas law essentially states that the density multiplied by this relationship, right? We have forgot what this constant is called, but this constant is approximately 8.314 joule per, you don't gotta know the units, right? Approximately 8.314, okay? Multiplied by the temperature divided by the molar mass of air. Okay, that's pressure. Let's go ahead and throw that in, okay? So velocity now becomes the square root of gamma multiplied, remember, pressure is going to be equal to all this. So we're going to multiply it by the density times, let's do this, the density times R times temperature divided by the molar mass of air. All of that is going to be divided by, right, we're just following this, all of that is going to be divided by the density. Close that square root. Oh, wait a minute. We can cancel out some things, right? Density appears on both sides of the fraction here, so we can just cancel that out. We can reorganize our equation to look like this. So gamma multiplied by RT, right? This molar mass is at the bottom of the fraction. It's just going to move down. Density's gone. So now this is no longer density dependent. All of that divided by molar mass. Okay? Let's continue. We're going to notice something. This is now, right? Let's go ahead and make us some room. We're going to move that right here. Let's continue working, right? Well, now we know all these values, right? So, like I said, this value is just going to be, there's a gnat in my room. This value is going to be 1.4, right? Now it's just plug and play. So 1.4. What did we say that r was? It's going to be 8, let's do parentheses, right? This is going to be 8.314 multiplied by the temperature. We'll just say 293. This is in Kelvin, by the way. All right, so 293. All of that is going to be divided by the the density of air. And that's going to be 0.02897, 0.02, I think, yeah, 0.02897. Let's go ahead and calculate that. So the square root of 1.4 times 8.314 times 293, all of that is going to be divided by 0.02897. Okay? I'm going around because I don't want to use all of those values. So we're going to say that this is approximately 343. Speed of sound, right? Speed of sound. Now we have that. What do we need next? Well, we need the relationship between E flat and A, right? We can tell that this relationship, well, it's a tritone, right? That was given. But what can we use out of that? So we'll take F prime as the frequency that Bissell is hearing and the frequency that Albert's actually hearing as F, right? Denote this more easily, we can just do E flat over A. This isn't a chord, it's just a relationship. We know that each time, right, there are 12 keys on a piano, and the relationship between each key as you go up in semitones is going to be 2 over 1/12, right? To go from A to E flat, you need to go up 6 times. So we're simply just going to raise this to the 6. And what does that give us? That gives us 6 over 12. We can do some simplifying and get that as 2 raised to the 1/2 power. What is that? That's simply just the square root of 2. How simple. What else do we need, right? We have speed of sound. We have the speed of sound. We have the frequency relationship. What else can we use? The general Doppler's problem, where I can just grab it from over here. Okay. Just go ahead and copy this. It's probably going to take the highlighter, but that's okay. I can just delete that. All right. Let's go ahead and put it over here. Okay. This is the general Doppler's equation. Okay. Oh my goodness. Okay. What is this saying? Okay. This is essentially saying that this is the frequency that Dr. Bissell is hearing. This is the frequency that you are singing. Albert is singing, right? This is the speed of the source. This is the speed of Dr. Bissell. And this is going to be the speed of sound. Albert is stationary. So this is going to be 0. So we're going to simplify this to the frequency is equal to speed of sound plus the velocity of Dr. Bissell divided by the speed of sound. All of that is multiplied by the actual frequency. We need the speed of this. This is the speed of Dr. Bissell, right? This is the one we need to find. So therefore, we can start rearranging this, right? So F prime over F. All I did was divide by frequency, and that gives us V observed over V, all right? Let's go ahead and multiply by V to get rid of this. Let's just move it to this side. So what we're going to get is we're going to get V multiplied by F prime over F is equal to V plus V observed. Okay? What do we need to do next? We need to move this to the other side. So we'll just subtract. We'll just subtract V. So what we're going to get is we're going to get V observed is equal to V F prime over F, all of that subtracted by that V. So now we have V observed completely on its own. So what can we do with this now, right? What can we do with this? Well, now it's just plug and play, isn't it? So we already saw that F prime over F is just E flat over A, which is just the square root of 2. So let's work through that. What do we know? The speed of Bissell is going to be the speed of sound, so 343 multiplied by that frequency relationship, square root of 2, minus that's, we can, let's go and factor that out, make our lives easier, right? It's just going to be this. Just like that, right? Here, I'll show that intermediary step. I'll do this. We're going to factor out that speed of sound. So we're going to get like this. Right? Boom. Exactly what I did. Then it's just plug and play. So let's go ahead and calculate that. So 343 meters per second multiplied by the square root of 2 minus 1. And we get 142 meters per second. Okay? Okay, well, what information does that give me, right? I'm American, bro. What is meters per second? So let's go ahead and figure that out. Okay? Meters per second to 2 miles per hour. Oh, that doesn't help me. Meters per second, 2 miles per hour. Okay, let's go ahead and change this value to 142. Okay, so that means that Dr. Bissell would have to be moving towards Albert at 317 miles per hour in order for him to hear that E flat if Albert is singing an A. And that's it.